Hello everyone, we are going to discuss now the radioactive decay of the three radioactive particles, namely the alpha particles, beta particles, and the gamma rays. So we are going to start with the alpha decay. And alpha decay is represented by this equation, where A is the mass number, Z is the proton number, X stands for the parent atom, and Y for the daughter nucleus. In an alpha decay, the nucleus loses 2 neutrons and 2 protons. The nucleon number goes down by 4. The proton number goes down by 2. So the nuclide changes to another element. Take a look at this example. The nucleus of an atom of radium-226 contains 88 protons and 138 neutrons. A radium-226 undergoes alpha decay to form a different element, which is radon-222 and an alpha particle. So, following the equation given, since radium has 226 mass number, if 4 will be deducted from it, it will give 222, which means that is the mass number of the daughter nucleus. Radium has 88 protons. So again, following the equation given, to get proton number of the daughter nucleus, 2 must be deducted from the proton number of radium. So 88 minus 2 is equal to 86. So an element having 86 protons is radon. After alpha decay of radium-226, it yields radon-222 and an alpha particle, which is represented by the helium atom in the equation having 2 protons and 4 nucleon or mass number. This periodic table is shown to help you picture out the table of elements. Now again, the elements having 88 protons is radium. So if we are going to deduct 2 protons from 88, it will give 86. And look at the periodic table. The element having 86 protons is radon. In this example, we are going to find out what is the parent nucleus, and that parent nucleus is represented by letter X in the first equation. Now, the daughter nucleus is given, which is lead 82 as its number of proton and 214 as its mass number. If we are going to add 2 to 82, it will become 84. Now, that 84 is the number of protons present in the parent atom. A daughter nucleus has 214 as its mass number. If we are going to add 4 to it, it will give 218. Again, the 218 is the number or is the mass number of the parent atom. Now, let us examine what element in the periodic table has 84 protons and 218 as its mass number. That is polonium. So let us proceed to the next page to find out in the periodic table if this is correct. So you will see here the two encircled elements. The first element is lead having 82 as its atomic number. Take note that again, the atomic number is equal to the number of protons. So, lead has 82 protons. If you are going to add 2 to find the parent atom, then it will become 84, and the parent atom is polonium. Let us now proceed to beta decay. As a result of beta decay, the nucleus has one less neutron but one extra proton. The atomic number, which is represented by letter Z, increases by 1, and the mass number, which is represented by A, stays the same. So that statement is represented by this equation. In this example, we need to find out the parent atom. Using the equation for beta decay, it tells that the daughter nucleus has more than one proton than its parent atom. So if the daughter nucleus has 83 protons, it means that the parent atom has 82 protons. Its nucleon number stays the same. An element having 82 protons is lead. Again, when lead undergoes decay, it yields bismuth plus a beta particle. This periodic table will help you again to identify the element having 82 protons, which is lead, followed by bismuth with 83 protons. We know that the elements in the periodic table is arranged according to its increasing atomic number, which is equal to the number of protons present in an element. In this example, polonium atom with 84 protons gain one more proton that makes it as thin as the daughter nucleus plus the beta particle which are produced during the beta decay. Gamma decay. Gamma decay is the emission of electromagnetic radiation from an unstable nucleus. Gamma radiation often occurs after a nucleus has emitted an alpha or beta particle. And this is represented by this equation. So take a look at the equation. Whatever is the parent atom, it will give the same daughter nucleus. Look at the example given. Cobalt-60 with excess energy decays to cobalt-60 with less energy plus gamma radiation. Take note that alpha particles and beta particles will not be given off in the same decay reaction. Alpha particles and gamma rays are possible together. Beta particles and gamma rays are possible together. But again, alpha and beta particles won't be given off in the same decay reaction. So that's all for radioactive decay. We are now going to proceed to the next topic, which is half-life. Radioactive decay is a random process. Remember, if we say random process, it is impossible for us to predict when an individual nucleus will decay. However, on average, there is a definite decay rate for each isotope. The decay rate is expressed as half-life, which is the time for the atoms in a sample to decay. Look at this decay model. The green squares represent the parent unstable nuclei. They decay into the red squares that represent the daughter nuclei. Look at the diagram. It starts from 16 radioactive atoms. When they undergo decay for the first time, they become 8. When 8 radioactive atoms undergo decay for the second time, it turns into half, which is 4, and the process goes on until it reaches 1 radioactive atom. Now, how many half-lives the 16 radioactive atoms undergo to turn it into 1? The answer is 4. Or simply count the arrows. An arrow represents 1 half-life. So 4 arrows represent 4 half-lives. The process is random. You can tell when a green will turn into a red or which green will decay. But after every half-life, half of the green parents will have decayed into red daughters. This is a radioactive decay graph of the given example. Always remember that in making a graph of the data, you must label all the axes. In this graph, the x-axis shows the number of half-lives and the y-axis shows the number of parent atoms left in a decay process. It is very important to write the title of the graph. So to explain this graph, the graph starts at 16 atoms and shows the number of parent nuclei having every half-life. All radioactive isotopes have decay curve that looks like this. However, the half-life times can vary from seconds to millions of years. The half-life of a radioactive element is the time taken for the activity to have, the number of parent nuclei to have, and the mass of the parent nuclei to have. Let us have some examples. Example 1. The half-life of a radioactive isotope is 27 years. How long will its mass take to fall from 2 grams to 0.25 grams? Take note that the decay starts from 2 grams. It was mentioned that the half-life is 27 years. So after 27 years, the 2 grams turn to 1 gram. We will continue the process. If it reaches another 27 years, 1 gram will become 0.5 grams. Another 27 years or another half-life takes place until the sample turns to 0.25 grams. So it will take 81 years for the 2 grams to fall to 0.25 grams. Example 2. The activity of an isotope falls from 600 becquerel to 150 becquerel in 10 days. What is its half-life? Take note that the activity of a radioactive isotope is the number of atoms that disintegrate or decay in 1 second. Activity is measured in becquerel, so 1 becquerel is equal to 1 decay per second. Go back with the problem. 600 becquerel falls to 150 becquerel in 10 days. Look at the solution. If we are going to have the 600 becquerel it will fall to 300 becquerel. And if we will continue it, 300 becquerel will fall to 150 becquerel. The problem tells that it takes 10 days to fall to 600 to 150 becquerel. It means that the half-life is equal to 5 days. Third example. An isotope has a half-life of 30 years. Estimate how long it will take for the number of nuclei to decay to 200 if the starting number is 8,000. Take note that the starting number is 8,000. If the half-life is 30 years, 8,000 will fall to 4,000 after 30 years. Years pass by. The 30 years is doubled and becomes 60. The 4,000 falls to 2,000. As the process continues, 2,000 falls to 1,000. And that is after 90 years. On its 120th year, 1,000 falls to 500. 500 falls to 250 after 150 years and falls to 125 after 180 years. So below 200 is somewhere between 150 and 180 years. If you will see on its 165th years, 250 turns to 187.5. That strengthens the answer, which is somewhere between 150 and 180 years. That's all, and I hope that this presentation helps you understand the lesson.